Okay, let's go over this homework. In the first problem, we have a function with x times y under a square root and x plus y in the denominator, and that gives us the conditions x times y greater than or equal to 0 and x plus y not equal to 0. And some of you are trying to put more complicated interpretations of those conditions in this definition of D, but I recommend just putting in these basic conditions, and then we'll make sure that we have D written correctly, and then we'll go down and figure out what these conditions really mean in order to graph. Now the condition x times y greater than or equal to 0 gives us two conditions. We have either they're both greater than or equal to 0, or they're both less than or equal to 0. And the idea is that they need to have the same sign, but we do allow for them to be equal to 0. And these two conditions give us the two regions shaded here. And then we go to the second condition, which gives us that y is not equal to negative x, which means that we're removing this diagonal. But the only part of that diagonal that can appear in our graph is at the origin. So we remove the origin as indicated by that open circle there. If you drew a dashed line going like this, I think that that also removes the origin, so that's fine. Okay, so now when we look at the graph from UPAT, we want to graph the function square root of x times y divided by x plus y. And I had some people making an error with where they put the parentheses or things like that. So I'm going to suggest defining f to be that function, and then we can actually see it and see that it matches with what we want. So that's just like a double check that you're typing it in that way. If you just do plot, then it just plots it without showing you the function. But if we do f colon equals what we want, then it'll display it there, and then we can plot that f with whatever with this hash 3D. But also I thought that we should be doing adaptive mesh equals 2, because if you don't put any adaptive mesh in there, I think it looks pretty bad, and even 1 is not as good as 2. So let's go ahead and graph with adaptive mesh equals 2, and we get something that looks like this. And then we see again with this standard view that it comes up with, we see how that corresponds with our domain. We have the quadrant here where x and y are both negative, that's this one, and then the quadrant where x and y are both positive is right there. For number 2, I gave you a function that has no y in it, which I probably shouldn't have done, but that's what I did. So we end up getting the condition x squared minus 4 greater than 0. That's what we need for the natural log to be defined, and so we can define our d like this. And once again, we go through and figure out what that condition really means, and you can look at the graph of x squared minus 4, or you can do some solving of nonlinear inequalities to see that we get the conditions x greater than 2 or x less than negative 2, and those regions are graphed on the plane like this. Anything where x is bigger than 2 gets this strip, and anything where x is less than negative 2 gives us this strip, and we draw dashed lines along that border to indicate that we're not including the order because it's strictly greater than or strictly less than. And then again, plotting that function, we see what happens when we have a function that has no y in it. What we end up getting is just a graph in x that gets drug along the y-axis. So we get a graph that looks like this shape, and again it does match up with the drawing of our domain. For number 3, we're looking to sketch a contour map of the function, and again you're thinking of taking slices parallel to the xy plane and seeing what they look like. And let's look at my solution here. A little bit of a problem. Unlike the graphs in standard position, this one we have to think about really rotating the plane to have the positive x-axis where we would normally have it. Now a lot of you just drew it kind of the way it would be viewed, and in that case I would indicate that the positive x-axis was over here. But if we think about rotating around to get that positive x-axis over here, we see that the taller piece of the graph should actually appear right here, and that's going to give us more contours. Because if you think about taking slices parallel to the xy plane, eventually we're going to miss that smaller hump and we're going to keep taking slices of the taller one. So we should end up with more circles there, and we get something that looks like that. For number 4, uh, again, we need to think about rotating that x-axis around over here. It's actually symmetric, so in this case it shouldn't matter too much. But in any case, when we're taking these slices across the xy plane or above the xy plane, um, we can think that they'll cut out in these little like U shapes. So these U shapes, and I drew some U shapes there, and it should be symmetric. You should be getting the same sort of shape um, on either side of the origin. And you can see that this thing is probably getting steeper as we go up, so maybe they should be getting closer together, but I'm not going to be too picky about that. So finally, for number 5, we're producing a contour map and a graph. I did the graph first, which I would recommend because you get to see what area you should be taking these slices in. This one turns out to give us a region that goes from z equals 0 to z equals 1. So that's really where we should be taking our contours, is from 0 to 1. And you'll see that I do that here with my contour range going from 0 to 1, and I chose a step of 0.1. That would give us about 10 contour lines, which we get here. Actually probably get 8, because at the very top we're just getting a single point, and at the very bottom we're kind of getting nothing. So we end up with those contours, and you see what's happening is, of course, it is getting steeper as we go up. So these contours are getting closer together, except for at the very top where we don't get the top of that cap.